Professor Arutyunov, can we proceed with the session? If you can hear us, can you let us know?
Please, can we start?
Yeah. Can you just let us know if you can hear us? Can you hear us?
Sorry.
Can you hear us?
Please give the talk to Sergei Zhukovsky. Switch off his microphone. Switch on his microphone. He will make the talk.
Okay. I think Sergey can. I think Professor Sergey can turn on the mic and camera.
Seriously.
You make go. Yes. Okay. So, can you let us know if you can hear us from this side? Then we can start.
Hello, dear colleagues. This talk, it is a joint talk. The authors are Professor Arutyunov and me, Sergei Zhukovsky. And the talk is devoted to...
Astier will introduce the speakers and then we can start immediately.
Okay.
Yeah. So, shall we start now? Yeah, so it's my pleasure to introduce our speaker, Professor Sergei Zhukovsky, and Professor Arutyunov. So they will speak on implicit function theorems and abnormality. So it's over to you, Professor Sergei.
Okay, hello. In this talk, we will discuss some recent results on implicit functions. In order to start, I would like to recall some known results concerning implicit function theorems. So let X and Y be Banach spaces, sigma be a topological space, and we are given a continuous mapping F. And we consider the following equation, equation 1. Here X is the unknown variable and sigma is a parameter. And the classical implicit function theorem states the following. If this mapping F is smooth enough around the given point x0, sigma 0, x0 is a solution to equation 1 when the value of the parameter is sigma 0. And the point x0, sigma 0 is normal, which means that the derivative of f in x at this point is a surjective linear operator. If all these assumptions hold, then there exists a local implicit function. Namely, there exists a neighborhood of sigma 0 and a continuous mapping G acting from this neighborhood to X, such that this mapping G solves equation 1. Namely, this identity holds. This result, various variants of these results were known at least since the end of 19th century for Banach spaces. This theorem was proved in the paper by Bartle and Graves. This assertion is of local nature, namely, I mean that the domain of this implicit function is a neighborhood of sigma 0. In the following theorem, the domain of implicit function is the entire space of parameters. Assume that the mapping F is differentiable in X at every point of the domain, and the mapping and its derivative are continuous. Assume that the derivative of F in X is an invertible linear operator at every point of the domain, and that the norm of inverse of this linear operator is bounded. Under these assumptions, the initial equation has the only solution G of sigma for every sigma, and moreover, the mapping which corresponds to sigma, this unique solution, is continuous. This result follows from the well-known Adamar theorem. For Banach spaces, this assertion was proved by Reinbold. These two theorems and some similar analogous result lead us to several questions. The first question is, what are the conditions for existence of implicit function when the point x0 sigma 0 in the local implicit function theorem is abnormal? Let me write some elementary example. Let f of x sigma be equal x1 square plus x2 square minus sigma. Obviously, let us take x0 is 0 point of R2 and sigma 0 is 0. Obviously, the derivative of f at the point x0 sigma 0 vanishes. So the assumptions of implicit function theorem fail to hold. And it can be easily seen that there is no implicit function defined in the neighborhood of sigma 0. Since this equation have no solutions when sigma is negative. Now, if we change the sign here, x1 square minus x2 square, then again, the derivative equals 0. However, in this case, the implicit function exists. And so the first question, what conditions can we find for existence of continuous implicit functions in abnormal case? And the second question concerns the global implicit function theorem. Here it is. In this theorem, there are two assumptions which can be weakened. The first one is the invertibility of the derivative. In the local implicit function theorem, this assumption is absent. In the local theorem, this linear operator is assumed to be only surjective. but not injective. And the second assumption, which is quite strong, is the uniform boundedness of this inverse. So the question is, how can we weaken these assumptions and preserve the existence of implicit function? And the answers are, some variants of answers are as follows. Let us start with implicit function theorem. As before, X and Y are Banach spaces, sigma is a topological spaces, and we are given a closed convex cone K in X. And we consider a little different problem. We consider the equation f of x sigma equals 0 and some additional constraint. We will search for solutions not in the entire domain X, but in the given cone K. Again, x0 and sigma 0 are given points, and f of x0 sigma 0 equals 0. Assume that f is smooth enough. Here is the smoothness assumption. I will not pay much attention to the details. The main part of this assumption is that f is twice continuous differentiable in X around the point x0 sigma 0. Assume additionally that linear shell of the set C is closed and topologically complemented. Here C is defined by this formula. So it is defined by the mapping F and given cone K. Since this linear shell is topologically complemented, there exists a projection of the space Y to this subspace. And we denote this projection by P. We will say that the mapping F is too regular at the point x0 sigma 0 if they're in the direction H. If H belongs to the set K, it also belongs to the kernel of this linear operator, and its second derivative satisfies this inclusion, and equality 5 holds. Equality 5 means that the linear operator, which consists of two parts, this is the first derivative, and this part is the second derivative, a quadratic mapping, for which the first argument is fixed, it is H. And it is written here that the image of this linear operator is the entire space Y. So let us now pass to local implicit function theorem. Assume that the relative internal of C is non-empty, and there exists H such that the mapping F is too regular at the point x0 sigma 0 with respect to the set K in the direction H. Then there exists an implicit function G, continuous implicit function in a neighborhood of sigma 0. And for this function, inequality 7 holds. The inequality looks quite unusual and complicated. Here delta 1 and delta 2 are defined by these equalities. So in order to simplify this, the statement of theorem, let us additionally assume that this set df over dx at point x0 sigma 0 applied to the cone K is a subspace. For example, if K is the entire space X, then this set is a subspace. In this case, the term delta 2 can be omitted, and estimate becomes a little simpler. If k coincide with x, then in theorem 1 we receive estimate 8. It contains two terms, the first order term and the second order term. Note that if the point x0 sigma 0 is normal, then the assumptions of theorem 1 and the assumptions of corollary 1 hold. Well, if the mapping is smooth enough. And in this case, f is too regular in the direction, in the zero direction. And in this case, this projection pi is a zero linear operator, and the second term disappears. And we obtain, in normal case, we obtain the standard estimate, which contains only the first term. Let us now pass to global implicit function theorems. Here we will use, again, we consider the same spaces and the same equation, and here we use the following notion. Covering constant of a linear operator A is this number. It is also called Banach constant, and by Banach open mapping theorem, this constant is positive if and only if the operator A is surjective. So I think that I am a little short in time, so I'll pass immediately to the main result of this part. Theorem 3. Assume that, as before, f is smooth enough, in particular, if x and y are finite dimensional spaces, then we just assume that f is continuously differentiable in variable x. And assume that all the covering constants are separated of the derivatives are separated from zero by a number, positive number a. Under this assumption, for every function phi continuous, there exists a closed implicit function g defined on the entire space sigma, and close means that this inequality in Formula 13, this inequality holds. This is the global version of implicit function theorem, and under additional assumptions, we can also obtain the uniqueness of this implicit function. So these results were partially published in the papers that you can see on the screen. And I think that I finished the talk. Thank you for your attention.
Thank you for your nice talk. So, Professor A.V.Arutyunov, you would speak something?
No, thank you.
Okay.
Everything is taught.
Okay, thank you. So, any question from offline and online participants? So, can you check, is there any question from online participants?
No, there is not.
Okay, so there is no question. So let us thank our speaker. Okay. Thank you.
Thank you.
Thank you.
So we have longer